Yeah, we could skip to chapter 10. So what we're going to do today is we're going to finish up chapter 5 and then just start a little bit in chapter 6. Chapter 6 is pretty short. We'll probably finish it either Monday or early Wednesday, which would mean that we're looking at a test not this coming week, but probably the following week on like Tuesday or Monday or Wednesday or something. But we'll find out more next week at the beginning. And then we won't have class on Friday next week because that's the day after Halloween, plus I have to go to a meeting. And I thought about scheduling the test on that Friday, and then I thought it's the day after Halloween. Jay's not that much of an asshole. You guys are welcome, so enjoy your Halloween. Before I forget, Haley, after class, let me know more about Saturday. And then my plans for the afternoon are, I've got a lunch meeting from 11 to 12, but I'll be back at 12 if people want to come in and ask questions. I will stay here as long as either people are asking questions or I get absolutely tired of you all, at which point, if I feel like any homicidal urges to kill anyone, I will go ride my horse because it's going to be a gorgeous day and I haven't gone riding all week. So I think that's fair. And I will also be here all weekend if someone wants to try to schedule a time in the middle of the week or something to discuss some of this. So let's take a look at where we left off. What we were doing is we were writing electron configurations for the elements. And so what this is really supposed to be doing is many-fold, meaning we use some specialized notation to represent it so that we're not having to draw ugly pictures, but that specialized notation represents many things. It represents the energy levels of the electrons. It really represents the location in three-dimensional space, if we can, kind of picture it or imagine it. Although I got to be honest, having a mental image beyond the s, p, and d orbitals and having like lots and lots of those orbitals filled up is not really necessary. What we have to be able to do really is look at using that notation to help us kind of decide and do other things. And so we were kind of looking at those. So let's just pull up an element, for instance. Let's see, which one do I want to pull up that's entertaining to start with? I don't like any of the ones that I got here. Let's pull up, I don't know, does anyone remember where we left off? I thought we had actually kind of finished, so maybe this is a bit of a review. Let's do, say, for instance, sodium. So how many electrons does sodium have? And where does that information reside in the universe? No one can tell me how many electrons sodium has. Do you have your periodic table in front of you? I was going to say, this is chemistry class. If you don't have that periodic table and cheat sheet handy most days, no good. So how many electrons then, Zach? 11. So we just get that straight off the periodic table. And then how do I know the order to fill the shells in? Because you have to know the order. You have to know that you go 1s2, then 2s2. Where do I know that? Where do I get that information from? Right, but what's after the 2s shell? Nope. So you can either look on your periodic table, remember, for that filling, or you can remember the little pyramid where it's 1s, 2s, 2p, 3s, 3p, 3d, where again we fill it like this. So after the 2s is the 2p. And then how do I know how many electrons go in each orbital? So I mean, just to write this question out, you have to know a lot about quantum mechanics. If any one of these steps is missing, then you get the problem wrong. So, even though it seems, reasonably simple on the surface, there's a lot of information entailed in this. So how many electrons per orbital? There's two places you get that. You can get it from your periodic table, or you can memorize it. And so we know that S has 2 electrons, P has 6. More fingers, Zach. D has 10, and F has 14. And so we know we can go 2p6, so we've used up 10 electrons, and so the 11th electron is just in that 3s orbital, and it's unpaired. And so if we draw this for an orbital picture, you know, we've got our 1s. Further out, we have our 2s. Then we've got our 2p, and then our 3s orbital. And we've got paired electrons in the first bunch of orbitals. And then we've got just one lone electron in that 3s orbital. So what we want to do at some point is this notation here, this sodium is 1s2 that. This has to be second nature, because we're going to use it to explain lots and lots of stuff, and we're going to be constantly referring back to it. The other thing we might want to know is the shorthand for it, because normally we don't care about the shells that are filled. And so we said that the shorthand for sodium would be to take the first set of orbitals that are completely filled, 1s2, 2s2, 2p6, and then what element does that represent? Yeah, that's neon, and so we can say it's got the same inner shell electrons as neon, and then its outer shell, or its outermost electron, is in that first orbital, so it's just 3s1. So also be fairly familiar with that shorthand notation. Again, we're going to use it a lot. I got to be honest, for the small elements, I tend to use the longhand notation anyway, because it's just as fast, and it's a little bit easier to see and understand and check. And I can never remember which one of these looks without getting a periodic table necessarily. Okay, so we have another feature that we can discuss about elements, and this is one of those interesting features. Some elements in their pure states are magnetic and some are not. So we have two types of magnetism. We've got diamagnetic, and that means that they do not contain unpaired electrons. Therefore, they're basically non-magnetic. Although technically they're slightly repelled. But that's another more complicated explanation, not worth worrying about. And we have substances that can be called paramagnetic. And this comes not so important in this chapter, but we'll come back to it at either the tail end of chapter 7 or chapter 8. I forget which chapter. And this is ones that contain unpaired electron spins. And so that means they're attracted to a magnetic field. And this is actually one of the ways that we came up with that Pauli exclusion principle and that Hund's rule, in that we can actually measure it and then know how it happens. For instance, if we take a look at helium, when we measure it, it's diamagnetic. So we knew that the electrons in its orbitals, in the 1s orbital, had to be paired up like that, meaning there's no unpaired spins. But, you know, if we take a look at lithium as a metal, we know that that's paramagnetic from measuring it. And so we were able to say, well, the way that electron orbitals have to go is that it has to have an unpaired electron. Or maybe more importantly, we can take a look at carbon, which has 1s, it's got 2 electrons in that, its 2s shell is filled. And then if you measure it, the magnetism is proportional to, like that. 1, 2, 3, 4, 5, 6. Yes, 6 electrons. The magnetic field is proportional to the number of unpaired electrons. And so, since carbon's paramagnetic, we knew that those electrons couldn't be paired up. And we knew that they had to be spin aligned, because if they were spin opposite, then they wouldn't have a magnetic field either. And so, from those magnetic measurements, they were able to kind of determine a lot of information about those elements. Now, if you look on your book on page 172, it lists the electron configuration for all elements, which is wonderful. I suggest, however, on the homework that you use this to check your answer, not write your answer. Meaning you don't get this table in your book or on your test. Instead, you have to have it. And so one of the things that you'll notice if you're going through that table is there are some exceptions to the rule. For instance, if you look at it and we write the electron configuration for chromium, using shorthand notation, it should be argon 4s2, 3d4, meaning this is the expected. But what we observe in nature, and from its ability to make bonds, is that it actually looks like Ar 4s1, 3d5. So notice in both cases it has 6 electrons in its outer shell. In the expected case, we would expect the s orbital to be full and the d orbital to have 4 unaligned spins. But what we observe is that really the d orbital is half full and the 4s1 orbital is full. So here we've got something that looks like this, and then we've got 1, 2, 3, 4. But what we observe, 4, 5, is that we really have 6 electrons that are all spin aligned in there. And the reason for that is that first off, the energy levels are very close together. Get very close together. And at high energy levels, or at high principal quantum numbers. And it turns out that a half-filled d orbital is lower in energy than a partially filled d orbital. So much so that instead of looking like this, where we would have our 4s orbital and our 3d orbital at slightly higher energy, instead, if they're half full, that 3d orbital drops down. And so we have our 4s and our 3d. And so that half-filled state allows it to do that. What this means, or what this helps explain, is the variable charges for many atoms, or for many of the metals. Meaning, if you look at a lot of the metals, for instance, chromium has a variable charge. Well, if its goal is to fill its orbitals, it can fill the 4s orbital with just 1 electron. So chromium plus 1 is pretty common. But it takes a lot more electrons to fill that d orbital. And so, the other normal state for chromium is like plus, I guess it would be 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, plus 6. And so chromium kind of has 2 oxidation states that it can be happy in. And actually it has many more than that, because those energy levels get so close together and they mix so much, and little tiny things can affect them, that the chemistry becomes complicated. So what we note is that chemistry of, for instance, the S block elements and the first row, and mostly the second row of the P blocks, is pretty simple. Meaning there's not very many exceptions. It follows the rules well. The chemistry of the D block elements, and basically anything with d orbitals, or basically the third plus row of the P block elements, is complicated. Because those energy levels are very close together. So one of the things you'll note is that for a lot of what we do when we talk about chemistry, we stick to elements that are in the S block. We stick to elements that are in the top end of the p block, especially if we're drawing structures and sharing electrons and doing things like that, and that we tend to ignore a lot of the stuff in the d block. Now, we still make use of those variable charge cations. We pick the well-behaved ones to play with, but really the chemistry gets much more complex the further down the periodic table. I don't know anyone, I've never taken a course, for instance, on lanthanide chemistry, like uranium and various things like that, or the actinide chemistry for the F block elements. I imagine it's quite complex and not terribly easy to do either. Half of the elements are radioactive, if nothing else. That always complicates matters. So realize that there are some exceptions to the rule. Another example of an exception to the rule is copper. For instance, what we expect, or what we would predict, would be that copper would look like argon with a 4s2 and a 3d9 shell. What we get experimentally, or what's real life, or what we actually measure, and this is why chemistry is an experimental science, meaning we can predict all sorts of things, and until you actually go and do the experiment to prove the prediction true, it's just a prediction. And how good a theory is usually depends on how well it can predict things. And, you know, the harder things are, the more complicated the theory has to get to be able to predict everything. And so, like I said, we usually have like very basic theories to start with, and then if we need to go on in chemistry, you'll get more and more complex theories. In real life, we see it look like argon 4s1 3d10, with the idea that a full d orbital is lower in energy than a full s orbital. So again, the orbits shift places, sort of depending upon if they're half full, and sort of depending if they're totally full. And so one of the things you can see is that this would predict, you know, that we could have a copper +1 ion pretty readily. And then we also have other charges of copper that work pretty well for it. And so, you know, we can also use the electron configurations to kind of predict the charges of different elements. Your book at the tail end of Chapter 5 talks about the size of atoms. Now, to me, that material really belongs in Chapter 6 because Chapter 6 is all about a series of periodic trends. And so that tail end of Chapter 5 kind of merges in with the beginning of Chapter 6. And so what we'll do is some of the information from the tail end of Chapter 5 will just fit into the Chapter 6 lecture. And so it's all mixed up. It's also mixed up like that on the homework. So for instance, if you're looking at a homework question on the size of an atom, realize that it might be on the Chapter 6 homework, but the information is actually in the Chapter 5 homework. Okay, one last thing I want to kind of do before I really kind of consider Chapter 5 complete. And your book has an excellent picture of this. I draw crappy pictures, so if you want, I'll put a reference up to it. On page 169, we talk about something called electron shielding. And what electron shielding is useful to explain is both the size of atoms, and it also helps to explain the energy levels and the mixing. We'll focus on this, and we'll just accept this as a fact, meaning we won't go to do the actual calculations would be problematic, and so we're not really going to worry about them too much. So if I take a look at an atom, I've got the nucleus, that's got our positive charge in it, and then what we're saying is that we've got these orbital shells full of electrons. And there's two types of forces kind of going on here. Between the electron and the nucleus, we have an attractive force, because we know that opposites attract. And then between electrons, in between the shells, we have a repulsive force. Because, of course, we know likes repel. I always tell myself that the reason that supermodels will never date me is because obviously likes repel and I'm just that handsome. No. I got one applause and a bunch of looks that said, what the frell is he trying to convince us of? So we've got these attractive forces and we've got these repulsive forces that are going on. And so what happens is that the electrons in the outer orbits, are shielded by the electrons in the inner orbits. And what that does is that decreases the attractive force and it sort of increases the repulsive force they feel. And so what that means is that different electrons sort of feel a different attractive force for the nucleus. For instance, s electrons are the most strongly attracted. Whereas because of their shape, the p orbitals are less strongly attracted. Same thing with the d and then the f. And so depending upon which one you have, they have lower energy levels. So what happens is our s orbitals actually shrink a tiny little bit. Our p orbitals actually increase in size just a tiny little bit. And so what that does for the energy levels is, you know, we said that certainly we should have the 1s is the lowest in energy, and then the 2s, and then the 2p were the same in energy. But what happens is due to that shielding, remember, we really know that the 1s is lowest in energy, then the 2s, and then the 2p is slightly higher in energy. So here's our energy, and here's our energy scale here. And so this helps to kind of explain why that we have that special order for filling the electron orbitals, why some are lower in energy than others and some are higher in energy than others. We've got this electron shielding going on. That also kind of is going to help explain sort of, for instance, when we get to the size of atoms. Mathematically, we can sort of describe this in an equation. And the equation that we like to use is we say that the Z effective is equal to Z actual minus the electron shielding. And so Z effective stands for the effective attractive force between the protons or the nucleus and an electron. Z actual is the actual attractive force. And of course, we subtract off that electron shielding because we realize that electrons in inner orbitals, shield electrons in outer orbitals. Therefore, they feel a less attractive force, or less of an attractive force. That also explains why, for instance, this is a negative sign in the equation, because they feel a smaller attractive force. Therefore, they're not as attracted to the nucleus. So what does that mean for the size of atoms? Well, what we're going to talk about for periodic trends are kind of twofold. We're always going to ask what happens as we go across a column, and we're always going to go ask what happens across a column, across a row, and down a column. So we can use this to talk about our periodic trends. Periodic trends. And we'll have a bunch of trends. And you don't have to memorize the atomic size of anything, but what you do have to think about is how the trend works and what atom is generally bigger than another atom. So the idea is that we want to know what happens to the size of an atom when one we go down a column, and 2, we go across a row. So the first one is by far the easiest. What do you think happens to the size of an atom as we go from, say, down a column? What I mean is if we compare lithium, or hydrogen, lithium, sodium, all the way on down to whatever's at the bottom of that column, francium. Where is the bigger and where is the smaller atoms in that? Gabe, Rod, any idea? Well, so what's bigger, hydrogen or sodium or francium? Or what's smaller? I mean, we can ask the same question in the reverse order. So this is smallest. This is going to be the biggest. Think about it this way. There's what's changing down a row or a column. So down a column, the principal quantum number increases. So for instance, for the hydrogen row, n equals 1 for hydrogen, right? For the lithium row, n is equal to 2. For the sodium row, n equals 3. And for francium, I don't know, that's so far down I got to count. Let's see, 1, 2, 3, 4, 5, 6, 7. n equals 7, right? And remember that that principal quantum number tells us the approximate size of the orbital. So for instance, if we take a look at a picture, the n equals 1 orbital is closest, the n equals 2 orbital is furthest out, and then, you know, excuse me, way out here we'd have our n equals 7 orbital. So going down a column, every time we go down a row on the periodic table or, you know, move down the column, our atoms are getting bigger and bigger and bigger. So hydrogen is actually a very tiny little atom. One of the reasons why hydrogen is the exception to many rules, first off, it's the only atom with 1 proton and 1 electron. And second off is its size plays a pretty big role in some of its properties. So going down a column, we expect, you know, down a column, size increases. So francium is a very large element. So hydrogen is a very small element. I'm going to move the across a row to a new slide just because, you know, otherwise I run out of room. So what happens across a row? What we mean, for instance, is to compare, say, lithium versus, what's on the other end of that row? Fluorine. Or, for instance, sodium versus chlorine. Which element is bigger? So think about what's happening as you go across a row. So there's sort of two things happening. We're increasing the number of electrons and we're increasing the number of protons. And so what happens is the increasing number of protons increases the attractive force, right? That was our Z effective, or Z actual, sorry. Increasing the number of electrons increases the repulsive force, but not a lot, because the electrons are in the same shell, meaning they're about the same distance out. And so that's our electron shielding term. And so if you kind of think about it, what happens is if I compare lithium here, you know, its outermost electron is in that second shell, versus, say, fluorine, where, you know, again, its outermost electrons are in that outer shell, and then, you know, there's some p orbitals in there. It's got some electrons in it. It's just got a lot more electrons in all its orbitals. There's a p electron. And so if you look at it, this has got 1 outer electron. This has got 1, 2, 3, 4, 5, 6, 7, if I drew it right, double check, 7 outer electrons. And so the attractive force is constantly increasing because we've got more and more protons in the center of the nucleus attracting it. The electron shielding term is about even because the electrons are all about the same distance from the nucleus. So what does that say about the size of an atom? If the attractive force increases, but the repulsive force is about the same. Think about it. So here's my atom. If the attractive forces increase, what happens to the size? Yeah, the electrons are drawn in. Now, we know that at the same time, every time we add an electron, we should be adding a repulsive force, right? But remember, when we're adding the electrons, we add one on this side and one on this side. They're not really very close to each other. It's only those inner shell electrons that are in between the nucleus and the outer shell electrons. And so the idea is that if we look at that, the effective attractive force, that's that Z actual minus the electron shielding force. Well, if this is increasing, this is approximately the same, then overall we're having an increasing attractive force. Therefore, the atoms shrink. So if we're summarizing it basically across a row, size decreases. They get smaller. That one's counterintuitive, I have to be honest. It really is, if you ask me. And a very good picture for that in your book, and again, this is that stuff where half of it's in Chapter 5, half of it's in Chapter 6, meaning I actually have my Chapter 6 notes open because I consider this more Chapter 6 material, but you know, it really is stuck at the tail end of Chapter 5. If you look at Figure 520 on page 177, that shows you a nice plot of the effective attractive force versus the atomic radius, and it kind of nicely explains that trend. So here's what you need to know for a test. There's certain levels of information. So first off, you can simply memorize it, meaning that size increases down a row or a column, and that size decreases across a row. You can simply memorize that. That's what I call level 1. That'll get you some points on the test. Level 2 is, can you explain why? So a test question might be, for instance, which is bigger? You know, sodium or, I don't know, what's in sodium's row? I'm having a blank. Sodium or, say, sulfur. And then, of course, the question will say, explain. So this is worth 1 point, because honestly, you got a 50-50 chance. The explain is probably worth 2 or 3 points. So really what I'm looking for is that level 2 learning. So go ahead and memorize the trend. That gets you at least started in the right direction, right? But you also have to think about this logically and be able to explain these trends. So what we're looking at is for you to have sort of a self-consistent view of how these different attractive and repulsive forces affect the size of molecules. We'll also talk about some other, you know, parts of it and not just focus completely on size. Okay, so the next thing we kind of want to look at, we'll take a little bit of a break from periodic trends, and the only reason I'm doing it in this order is this is how your book does it, and I don't want to get too far away from your book. Let's talk about common charges on atoms. And then what we're going to do is we're going to transition that to the formation of ionic compounds. Now, we sort of already know why ionic compounds form. We know it's the balancing of charges. But so far, you were told, hey, guess what? Just go memorize the damn charges. Well, wonderful. Not memorize them. I'm sorry. You have them on your cheat sheet. You don't have to memorize them. You were just told these are the charges. You weren't told why. So we're going to look a little bit at the y. And then we also said that, you know, these charges balance, and we want to talk about, you know, why the charges have to balance to a certain extent. And so we're going to take some information we already know and hopefully layer on another level of why it occurs this way. So you know how to use it. You know the answer to all the questions. Now I want you to be able to tell me why that's the answer to the question. So for example, why is Na a +1 cation? Or we could say, why is fluorine a -1 anion? And the reasoning behind this is that we find that the most stable elements, that is the noble gases, have one thing in common. That is, they have full electron shells in the s and p orbitals. Now technically they also have full electron shells in the d and f orbitals, but as you get down in the noble gases, they become a little bit less noble, and they, you know, violate those rules just a little bit. And so, you know, when we talk about this, we're really going to focus on those s and p electrons, or those electrons in those s and p orbitals. We have a special term for those. They're called valence electrons. So these are simply the number of electrons in the outermost s and p orbitals. Now you can extend this definition to include d orbitals, but again, it gets so complicated that we're not going to do it. And I don't even know if it really obeys it terribly well, even if you did try to extend it to that level. So we can explain why sodium forms a +1 cation and why fluorine forms a -1 anion by kind of keeping track of the valence electrons, or keeping track of the electrons in their outermost shell, and also comparing that with the noble gases. So for instance, if I pick on sodium, we've already done that one. That's 1s2, 2s2, 2p6, 3s1. And so what we say is that that has one valence electron, and because there's one electron in its outermost orbital, meaning that these orbitals here are completely full. And so remember, we can also write sodium like this. We said that it can be neon 3s1. And see, that neon is a noble gas with full orbitals. And it turns out that that is super stable. And so the goal for sodium in a reaction is to look like neon. Meaning, sodium really wants to lose an electron. It turns out that that electron that's floating out there in space, so here's sodium. And again, notice I'm using the Bohr model practically, right? Meaning I'm not drawing fancy electron orbitals. I'm not even representing it as waves. I've got 2 electrons in this orbital. I've got 8 electrons in this orbital, because remember, this is my 1s, this is the 2s, 2p, there's my 3s orbital. I've got 1 electron out here all by itself. It's furthest away from the nucleus. It feels the attractive force of the nucleus the least, so it's the easiest electron to simply remove. And it turns out that if you do quantum mechanic calculations, it turns out that when you have a completely full orbital like this, kind of like when we had the half-filled d orbitals and the fully filled d orbitals and our exceptions to the rule, that that is an extremely stable state for an atom. That it's almost impossible to remove an electron from a full orbital down here, meaning it's really easy to remove that electron, it's really hard to remove that electron. So sodium loses one electron really easily because it wants a noble gas configuration. Now, if it wanted to fill that shell, how many more electrons does it need? I should point out that sometimes this valence electrons, this is also called the Octet Rule. What does oct mean? 8. It means all elements want 8 electrons in its outer shell because it's full. That's what the Octet Rule states. So how many electrons would sodium need to find? 7. What are the chances it can find 7 electrons? And even if it finds 7 electrons, remember, it only still has those 11 protons in the nucleus to keep track of it, right? So the idea is sodium, it's easier to lose 1 electron and reach that noble gas state than it is to find 7 electrons. And so a lot of chemistry is simply how easy it is to get that octet. Fluorine's the opposite. If we look at it, it's 1s2, 2s2, 2p5. So how many valence electrons does fluorine have? It has 7 valence electrons, meaning this is the outermost orbital, and it has 7. Or if we're looking at that picture, here's my 1s orbital, and it's got 2 electrons. Here's my 2s and 2p orbitals, and there's 7 electrons. So remember, its goal is to look, like a noble metal or a noble gas. And what that really means is that it wants 8 electrons in its outer orbital. So for fluorine, it just has to gain 1 electron to do that. And so fluorine loves to gain an electron. Fluorine's most stable state is fluorine -1. I don't even think there is such a thing as fluorine -2, because what would it have to do then? It would gain an electron, right? It would have its full orbital, and then it would gain 1 more electron that would be all out there, all by itself in its orbital. Like if it had to gain another electron, it would be way out in that 3s, 3p orbital, and there wouldn't be much attractive force to the nucleus, and it's just unlikely to occur. So the idea is that the common charges we see on all the elements are simply a function of trying to look like a noble gas or trying to have that octet rule satisfied, or basically having completely filled outer shells. For example, what's the electron state for, say, oxygen? It's 1s2, 2s2, 2p4. Make sure I'm not screwing up. Yep. What does it want to do? It has 6 valence electrons. Therefore, it wants to gain 2 electrons to form oxygen 2-. And what's the state that we said oxygen is always at? In this class, we said it's always -2, right? We said there are some compounds where it really has a -1 charge, but that we're not going to talk about those. And so there are obviously exceptions to every rule in chemistry, unfortunately. It makes me wonder why we call them rules. They really should be just chemistry rules of thumb or something, or chemistry approximations. It's most often like this, not actual rules. And it also explains why ionic compounds form. They form because 2 elements can have a noble gas configuration, or a noble gas structure, or another way to say that is they can both fulfill the octet rule, fulfill whatever, the octet rule. If I take a sodium that has 1s2, 2s2, 2p6, 3s1, plus a fluorine that looks like 1s2, 2s2, 2p5, well, if this electron from sodium goes to fill that orbital, then on the other side, when I look at that sodium fluoride compound, with the +1 and the -1 charge, then sodium really looks like 1s2, 2s2, 2p6. Fluorine looks like 1s2, 2s2, 2p6. They both have octets. or basically 8 electrons in the outer shells. One of the weird things I think about chemistry is it's nice to understand the reasoning behind the octet rule. It's nice to see how the orbitals predict it and stuff like that. But they certainly knew about this octet rule well before they knew about quantum mechanics. We'll talk about in chapter 7 called Lewis structure theory, or Lewis structures, where basically Lewis came up with a series of rules for how to share electrons between atoms that would allow us to predict what elements or what compounds are stable. Like, for instance, we've said that we can make carbon monoxide, right? We can have carbon dioxide, but we don't make carbon trioxide. Or we can have H2O, but we don't necessarily have just HO. And so there's some rules for doing that. There's some rules for sharing electrons. The biggest rule for that we actually learned in this chapter. That's the octet rule. And for Lewis, it was just an observation. And it wasn't until quantum mechanics could explain where the electrons are and how many different types of orbitals there are that we could actually see where that rule came from. So that's the tail end of chapter 5 and the beginning of chapter 6. We'll maybe cover one more topic. I think that's enough to let you do chapter 6A homework, and if it's not, we won't do it. And it dovetails in with what we've been talking about, where we talked about the size of atoms. Now we want to talk about the size of the cations and anions. And again, this is just an exercise to a certain extent in having a visual picture of what's happening, of these electron orbitals, understanding those attractive and repulsive forces, and then being able to apply them to a problem. And so again, just like the size of atoms, there's 2 levels. Memorize the rule if you want. Wonderful. That's level 1. And then apply the rule. That's kind of level 1, 2. Explain the rule. That's level 2. So what happens for cations? Meaning, is sodium or sodium plus 1 bigger? And of course, we can ask the exact same thing for anions, in which we're saying, is fluorine or fluorine minus 1 bigger? So what happens to an atom when it gains an electron, and what happens to the size of an atom when it loses an electron? What do you guys think? What? Cations or anions are bigger. So a cation is bigger than a normal element. That makes sense, right? If we look at it, sodium has 11 protons and 11 electrons, right? Sodium plus 1 has 11 protons and 10 electrons. So there's a bigger attractive force for each electron. Therefore, the atom shrinks. So the idea is that cations are smaller than atoms, than the neutral atom. And then, of course, it seems like it would make sense then the opposite is true. So, for instance, fluorine has, it's 7, right? Yep. See, I'm doubting myself today. I mean, it's 9. See right there. 9 protons, 9 electrons. Well, if I have 9 protons and 10 electrons, then each electron feels less of an attractive force. Therefore, the atom gets bigger. And so we find that anions are larger than atoms. And so if we kind of stick those together, and I'll put it on the same page, even though it should kind of go down below, the idea is that cations are smaller than neutral atoms, and anions are bigger than neutral atoms. So in general, anions are always much larger than cations in a molecule. Okay, I think that's a good place to end. Let me grab the chapter 6 homework real quick, make sure I actually give it to us. No, I'm just checking to make sure that you can answer the X and all those questions. I think you can. so we'll end it here today. So here's what we're looking at for next week. We've got Monday, Tuesday, Wednesday, and Thursday. This will be Chapter 6. This will be Chapter 6. This will be Finish, Experiment, X. And then Thursday, honestly, I'm not sure what we'll do. And then the week after that, we're probably looking at test on Tuesday. Now, maybe the test will end up on Wednesday. I don't know. It won't be on Monday because I want to give you guys a chance to ask me questions after studying for the weekend. The other thing we have to realize is that, let's see. On Tuesday, then, we'll have due homework 5. What was the last letter that we're on? We did A, B, C. We did E. Wait, A, B, C. Then we did D and E. So we should be on 5F. And 6A would be due on Tuesday. Does that seem about right? Okay, that's it for me. Let me go ahead and just save the lecture so that it doesn't crash or keep recording. And then, you guys are free to ask me questions until 11 o'clock. As I said, I'll be back at noon-ish. I guess I'll